Homework last night was page 652, number 2, and 5 to 11. Any issues with any of those questions, please? Number 7. Any others? Dane? 6. We got 6, 7. Is that it? Okay, 6 and 7 it is. Question 6 says, using a similar approach to Michelson, a student sets up a 64-sided mirror. Probably want to circle that because that's definitely not the standard number of sides for the mirror. Okay, we get in that habit of using 8 sides, either multiplying or divided by 8. We're 8 kilometers away from a fixed mirror. We're also a lot closer than we normally are in a Michelson experiment, right? 8 kilometers away, which of course we have to double. We want to find the frequency of rotation necessary to measure the speed of light. So it's the same type of problem. We just got to recognize that we're dealing with numbers that are quite a bit different than we're used to dealing with. Let's say that the distance is going to be 8. No, not going to be 8. It's going to be 16,000 meters. We're looking for the frequency here. Is there anything else if we read between the lines? Yeah. If we want to successfully measure the speed of light, then we're going to measure the speed of light to be 3.00 times 10 to the 8 meters per second. So we're going to have to assume the actual value of the speed of light, or the accepted value for the speed of light. Here's my 2 equations. D over t, t is equal to 1 over f. We plug in some numbers if we have them here. We got 3 times 10 to the 8. We got a distance here, 16,000 meters. That allows me to solve for little t. Go figure, that's not the time that I want. I want big T if I want to find frequency. But what does little t equal there? 16,000 divided by 3 times 10 to the 8. It's going to be 5.33. 10 to the negative 5.33 times 10 to the negative 5 seconds. Remember we said we're usually getting a 10 to the minus 4? Why do we get something that's quite a bit different here? You know, off by a factor of 10, basically. Yeah, I mean, all bets are off, right? All bets are off when we're dealing with numbers that are so different than we're used to dealing with. 64 sides, 8 kilometers. Don't expect to get any numbers in here that are similar to what you're used to seeing here. Frequency, I'm not sure what the frequency is going to end up being here, okay? I'm not going to predict anything. 500, 600, 5,000, I'm not going to predict anything because the numbers are so far off of what we're used to here. All right, let's rearrange this equation. 1 over the period here. It's 1 over 5.33 times 10 to the minus 5 seconds. What do you end up getting there? Oh, yeah. Sorry, made a mistake. Made it on purpose, just to see if you guys would catch it. Good for you, you passed. What do I do with this? Multiply it by 8, that's right. 64. No, you didn't let me finish. I was going to say multiply it by 8, and by 8 again. And then that means multiply it by 64, right? Okay, if you just let me finish, then I would have gotten to that. Okay, when we multiply that by 64, we get big T, which ends up being 0.0034, 341. Okay, we're going to say 1 over 0.00341 seconds, and what does that give me? 293 hertz. So it's not actually all that far off of what we would expect to get in most of the questions, right? In essence, I guess we got one number that's way off, another number that's way off. So what do we end up getting? They almost cancel each other, right? And we get a frequency that's fairly close to what we're used to getting. Is that okay? Okay, let's take a look at number 7 now. It says a 16-sided set of rotating mirrors is used to measure the time that it takes light to travel a certain distance. At what frequency does the mirror need to rotate such that it makes 1/16th of a revolution in the time that it takes the light to travel 3.5 kilometers and back again? So my distance here is 3.5 kilometers times 2, there and back again. They throw in this wording here, which is kind of meant to throw us off, I think, a little bit. Makes 1/16th of a revolution in the time that it takes the light to travel there. Isn't that what it always does? Except it's usually 1/8 of a revolution. So we're not changing anything with that, right? Just the wording of the question makes it look a little bit different, but it's not really any different other than the actual numbers. All right, let's solve this one now. We've got a distance here for number 2 of 7,000 meters. We're looking for the frequency. And again, If we're not given the speed, then we have to assume a certain speed, and the only one that we can assume is going to be the accepted value for the speed of light, which is 3 times 10 to the 8 meters per second. Let's write down our two equations. D over T, T is equal to 1 over F. Plug in what we have. We're going to say 3 times 10 to the 8 is the speed. The distance here is going to be 7,000 meters. What do we get for the time there? .33, 10 to the negative, thank you. 2.33 times 10 to the minus 5 seconds. We multiply that by 8 times 2, or we multiply that by 16, right? I shouldn't say that because you're going to start thinking, well, why would we do 8 and then 2? We're going to multiply by 16, right, the number of sides. What do we get for that? Okay, which we're going to turn around and take the inverse of that, 3.73 times 10 to the minus 4. A quick little way to do that on your calculator, by the way, is just to go 3.73 times 10 to the minus 4, x to the minus 1. It does exactly the same thing. What do we get for that? Now, this is a number that's quite a bit different than we're used to getting for the frequency, right? But that's okay. In a question like this, that's okay to get a number that's quite a bit different, because when we're dealing with a 16-sided mirror and a 3.5 kilometer distance, we're not necessarily expecting those typical numbers. We weren't in question number 6 either. It just happened that we got one that was pretty typical, or fairly typical. We weren't expecting it. Number 7, we weren't expecting it. We didn't get it. Okay, it's okay. We don't have to go back and say, what did we do wrong? All right? Okay, let's take a look at what we were doing here yesterday with the mirror diagrams. We'll spend a couple of quick minutes going over a couple of the mirror diagrams that we've already drawn. Okay, I'm not going to ask you to redraw these. I'll just redraw them to show you the rules or refresh your memory on the rules. Then we'll draw a couple of the ones from the back side of the page on those convex mirrors, the ones that are thicker in the edges, thicker in the middle than they are at the edges. This is our concave mirror. Okay, I want to draw an object right here. Let's put it in between. What's this point here called? That's the focal point. This would be the center of curvature if I made that mirror a complete circle. And we know the center of curvature of the mirror is twice as far out as the focal point is. So once we start doing some math on this on Monday, we're going to say C is equal to 2F. The value of C is equal to 2 times the value of F. All right, we got 3 rays that we can draw here to figure out what the image is going to look like. But we're only going to need to draw 2 of them for this particular diagram. First one is going to go parallel to the principal axis, and it's going to go where from that? It's going to reflect down through the focal point. The second ray is going to go from the top of the object to where? To the focal point, and then it's going to reflect where? Straight back parallel to the principal axis. My image is going to be formed right here. What are the 3 characteristics of that image? Is it larger than the object? Is it smaller than the object? Or is it the same size as the object? Looks to be a little bit bigger, right? So we're going to say it's larger. Number 2, is it right side up or is it upside down? It's upside down. We're going to say it's inverted, although, again, you can use whatever word you want for that as long as it means the same thing as inverted. Number 3, is it real or virtual? It's real. What does that mean, by the way, if it's real? We can project it onto a screen, just like the image literally that you're viewing right now on the smartboard. It can be projected onto a screen. Now, how do we know it's a real image? Solid lines intersecting. If it's dotted lines intersecting, it's going to be a virtual image. All right, let's take a look at 2 more quick ones here. This one's right at the focal point. First ray, just the same as the last one, is going to go parallel, then down through the focal point. Second ray, this time, we're going to go up away from the center of curvature, hits the mirror, reflects back upon itself. Where do those guys intersect? They don't. So let's extend them. Do they intersect back here? No, they don't. So what do we know about this image? There is no image. Let's do one more here. This time we've got our object inside the focal point. Okay, it's really, really close to the mirror this time. First ray, we're going to draw parallel to the principal axis, down through the focal point. That's the one we always do, right? Okay, we always do that ray. Second one, we're going to go up from the center of curvature, and then it's going to go back down, reflect back down in the same direction from which it came. They don't intersect on the left-hand side, so let's extend the reflected rays. They intersect over here somewhere. What do you know about this characteristic, the characteristics of this image? It's larger, yeah, it's upright, and it's virtual, meaning that you can't project it onto a screen. How do you see it if you can't put it on a screen? Look in the mirror. Right? You look in the mirror, you see a virtual image. That's what you saw this morning when you looked in the mirror in the bathroom, a virtual image of yourself. It's not that you can't see it, it's just that you can't put it onto a screen like you can a real image. Okay, we know it's a virtual image because it's dotted lines that intersect. All right? This is a convex mirror. In a convex mirror, we can draw three rays, but there's only two that we ever need to draw, and it's the same two, so I'm not even going to teach you the third one. The first two are always going to work for us. I'm going to draw one ray diagram here, and then you're going to be able to draw the next four because they end up all being the same. It doesn't matter where I put my object. Since it's the first one that I'm drawing, I'm going to put it way out here. I'm going to put it way out beyond twice the focal length. The two rays that I'm going to draw, first one parallel to the principal axis. We talked about this a little bit yesterday, right? Where does it reflect? It doesn't go down here, but it also doesn't go down here because it can't go down there, right? It's a mirror. It has to reflect, not go through. So where does it go? It goes up away from the focal point. So if this is the focal point, it's going up like this. It's diverging away from the focal point, not converging towards. That's why we say the convex mirror is a diverging mirror. Where's the second ray that we draw before you take off? Down toward the focal point. Doesn't go all the way down to the focal point. Okay, it's like it's going down there, but it stops when it hits the mirror, and then it reflects back parallel to the principal axis. Let's extend these rays because they're not intersecting on the left-hand side. So let's extend them. This one gets extended back to the focal point. This one gets extended back parallel to the principal axis. They intersect right there. What do we see? It is smaller, it's upright, and it is virtual. Get it? I'd like you, please, this weekend, on your long weekend, to please draw the last four ray diagrams for this. There's no tricks to it. They're all going to be the same as this. The image will look slightly different, but it's going to have the exact same characteristics. So please do that for Monday, please. Have a good weekend, everyone.